characteristics. So roughly 3.8, say 3.8, roughly 4 H bonds per water molecule. But you can see a dramatic decrease of the number of H bonds when water molecules enter the membrane. Basically, the number drops down to 3 approximately. So it means that each water molecule loses 1 H bond. So this is very, very important because from the thermodynamic point of view, it is a very, very unfavorable condition. And if you compute the interaction energy, if you focus first on the blue line here, it shows you that there is an energetic penalty, rather important, associated with the loss of hydrogen bonds. So, at first sight, water should not enter so easily inside the membrane. But the reason why it happens is that if you compute the interaction energy between water molecules that are confined inside the polymer and the polymer itself, you obtain a rather high negative, that is attractive interaction energy, and the answer is that actually this very strong attractive interaction between water molecules and polyamide overcompensates the energetic penalty associated with the loss of hydrogen bonds. And that's why this kind of system can take so much water inside. So that's very important if we focus on reverse osmosis to understand at the molecular level the transport of water through reverse osmosis membranes. In the next slide, we focus, this is a very recent work, actually, we have just published it a couple of weeks ago. Here we were interested on the behavior of still this polyamide membrane, but the behavior with respect to organics. And if you perform experiments, so this is an experiment, this is the rejection rate, the percentage or the fraction of solute rejected by the membrane. For instance, you have 0.99, this is 99% of the solute is rejected by the membrane. And if you do the experiment with these 3 organic solutes, you have quite different results, actually. So the behavior is quite different, which is a bit surprising because the 3 organics were chosen because they have exactly the same molar mass, molecular weight, okay? But if you perform molecular simulations of the system, and if you compute the relative affinity of the different solutes toward the membrane phase, then you observe a clear correlation between the affinity for the membrane phase and the rejection, the experimental rejection. Since, as you can see here, for the methyl isobutyl ketone, we have a rather strong attractive interaction, and it means a relatively high affinity toward the membrane phase, as this is related to a lower rejection rate. On the other hand, the affinity for the 4-aminopiperidine towards the polyamide membrane is rather low, and this is associated, or it corresponds to an experimentally to a high or rather high rejection rate. So there is a clear correlation between simulation and experiments. Well, that was for the good points of molecular simulations, but we must admit that these tools have also their limits, of course, and the limits is actually, as I said before, related to the computational resource. In other words, the simulation times are very, very limited. In this example, we were interested in investigating the desalination of seawater. So we considered a sodium chloride solution, still add the walls onto the system on both ends, and use these walls as piston, just to simulate the real reverse osmosis process. So this snapshot shows the initial configuration of the system with all ions. They are shown by the blue and the green balls here. All ions located, of course, on the same side of the membrane, and then we push onto the left wall, okay, to filtrate the solution. And this is the snapshot after 60 nanoseconds of simulation. You can see that not even a single ion entered the membrane after 60 nanoseconds of simulation. To give you an idea, with this kind of system, for system of this size, 60 nanoseconds represents approximately 2 months of calculation with multi-parallel computers. Okay? Well, you can easily understand that you have a problem if you are interested in investigating ion transport through polymer membranes with these tools, because ions they don't enter into the membrane. Okay? If you consider typical experimental fluxes, water flux through this kind of system, and if you consider rejection rates, say, between 95 and 99%, based on the literature, then actually you can estimate, you can assess that the time required to see a single pair of ions crossing the membrane should be between 800 nanoseconds and 4 microseconds. So if you look at this correspondence, 60 nanoseconds equals 2 months, then the conclusion is that it's not possible. Today, it's not possible to use this kind of tools to investigate solute transport through so dense materials. The problem is the density of the materials. Okay, in that case, you don't have any other choice. The only choice you have is to use different tools and to investigate transport at a much bigger scale. Then you will be able to explore much longer time scale. But of course, there is a price to pay. The price to pay will be a great loss of details. Forget anything about hydrogen bonds and something like this. It won't be possible to simulate this kind of things at the same scale. But we don't have any other choice. Well, I think that if we are talking now about macroscopic modeling, continuum-based theories, maybe the term is more appropriate, continuum-based theories, probably what is known as the space charge model or the space charge theory is probably the most sophisticated approach, I think. If you are from the field of microfluidics, nanofluidics, then you can also use the term Poisson-Nernst-Planck theory. So this is exactly the same thing as space charge model. So this approach is based typically on 3 governing equations. The first one describes the solute flux. In our case, could be, for instance, the ion flux through the membrane. So this is the so-called extended Nernst-Planck equation, considering flux as a result of diffusion, electromigration, and convection. You can see here for the fluid flow the Navier-Stokes equation, or more exactly the Stokes equation in this case. And of course, since we are dealing with ions flowing through membranes that can have a surface charge, as Patrick said, then we have to deal with an electrostatic problem, electrostatic interactions. And at this level of theory, this is a mean field approach, if you are talking about electrostatic interactions, then you have to deal with the Poisson equation. So basically, this approach consists in solving the system of highly coupled and highly non-linear differential equations. So this is actually quite tricky to do. It's possible to do it, but if you are interested in I would say, in real application, if you focus on industrially relevant conditions, I mean solutions with many kinds of ions, many kinds of solute inside, this is extremely complicated. And as a consequence, if you look at the literature, probably 99.9% of papers that are published in that field, they don't use this approach, strictly speaking, but only approximate versions, simplified models. Okay, just a slide to show you how complex is transport through membranes. This is a simulation that was performed considering a mixture of three different kinds of electrolytes and a total of 4 different ions. Potassium ions, sodium, chloride, and calcium. So this is not really representative of an industrial water. This is only 4 different kinds of ions. And if you look at the results, so this is the rejection rate as a function of the flux through the membrane. In this first example, you see, let's focus on calcium. You see that calcium is the least rejected cations. Then we have sodium, and the largest, the greatest rejection is for potassium. Calcium is the least rejected ions. Now, if you just increase the concentration of potassium chloride by 10-fold increase, now you see that calcium is more rejected than sodium, but it is still less rejected than potassium. And if you still increase the concentration of potassium chloride, once again by factor 10, this time calcium is the most rejected. So you can have third position, second position, first position, just by changing the concentration of another electrolyte in the system. So this is just to show you how complex can it be. Nevertheless, these tools, these macroscopic tools, can be very, very efficient if you are, say, interested in a, qualitative description of transport. Maybe not quantitative, but qualitative description. This is an example we obtained. It was a work we done a couple of years ago with a company. that was interested, can you do something for us with your models? Okay, so let's try. The problem was quite complex because actually in their solution there was many species, but some of them, most of them were at a trace level, and it was not so important for the industrial problem. But nevertheless, the solution contained at least 7 major ions: calcium, sodium, potassium, magnesium, chloride, sulfate, citrate, and also 2 different sugars, and many other traces. Never mind. And here you have the results of the modeling work we did. The blue bars show the experimental rejections of the different solutes, and in red you have the prediction of the model. This kind of macroscopic study. No more molecular dynamic simulations, absolutely not possible to apply for such systems. And you see that the agreement is actually quite good. You are even able to predict negative rejection. Right? You can be, if you are not familiar with membrane technology, you can be surprised by these negative values, but they are observed experimentally. So this phenomenon does exist really, and we are able to predict it, not quantitatively, but at least qualitatively. Well, the last thing I'd like to show you is quite recent work we did. We actually realized that most people, when they are involved in modeling, they always use the same assumption in their model. And this assumption is that the surface charge is constant over the membrane thickness, over the skin layer thickness. It means, if you think like a chemist, it means that intrinsically you assume that the functional groups that can generate the surface charge, you assume that these functional groups are homogeneously distributed inside the pores. Well, maybe, it might be, but for sure it won't happen for any kind of material. So what we did was just to modify the theory, the approach, in order to take into account heterogeneous distribution of the functional groups, just like this with monopolar distribution. All groups are negatively charged, but the local concentrations of the groups can be different in some part of the membrane. Or you can also focus on bipolar charge distribution. In that case, you have 2 different kinds of groups, 2, 3, 4, depends, but some of the groups are negatively charged, and some other part of the membrane are positively charged. Okay, and what we conclude from modeling is that if you use this kind of bipolar charge distribution, it seems, though, so this, once again, this is only simulation, but the rejection you predict as a function of Peclet number is a dimensionless number used mostly used in chemical engineering, because if the value is much larger than 1, the transport is mainly convective, and if you are below than 1, the transport is mainly diffusive. So for real application of reverse osmosis and nanofiltration, this part that is very important, because transport is essentially diffusive. And what we concluded is that if you consider the membranes with bipolar charge distribution, so if chemists are able to control the location of the functional groups, then we predict that these membranes should be as efficient for electrolytes with divalent cations than for electrolytes with divalent anions. And this is absolutely not the case with standard membranes. If you have membranes with constant charge density, with surface groups that are homogeneously distributed, you have either membranes very efficient to remove, for instance, calcium, but in that case, the rejection of sulfate will be rather low, or you have the opposite if you just reverse the surface charge. But in principle, if you can synthesize bipolar charge membranes, then you could be able to reject all these kinds of electrolytes in a very efficient way. And what is interesting is that I found in the literature, so this is experiment that was not done in our group, but by those guys, I don't remember where they come from. Maybe this guy is from Australia. Well, never mind, I don't remember exactly. And but this is very interesting because on the left, they performed a rejection experiment with a positively charged membrane. And of course, they observed that this membrane rejects very efficiently divalent calcium ions. Calcium chloride is highly rejected. But the membrane was not able to reject efficiently sodium sulfate. Okay? Then after that, they modified the membrane and they coated the membrane with a negatively charged polymer. Speak is a negatively charged polymer. So in a sense, they create a kind of bipolar system. And after modification, you can see that the rejection of both calcium ions and sodium sulfate were very high. So this is the experimental evidence of what we observed. Well, the last results is this one. Here we focused on the optimization of pore geometry, yeah, to improve membrane separation performance. In this context, in this work, we did not focus on the quality of the separation, but on the energy required to operate the separation. So what we did was to choose some target rejection value. For instance, if we want to reach 80% rejection, how much pressure should we apply? What should be the pressure difference to apply to the membrane? And we consider different systems: cylindrical nanopores, conical nanopores with a divergent or convergent shape, and this kind of biconical pores with this hourglass shape. Okay, and what we observe is that for all cases, the pressure difference that is required to reach the target rejection is always much lower if you use these hourglass shaped pore. Okay, this was done by this was observed independent of the surface charge density of the membrane, independent of the pore size of the system, independent of the type of electrolytes you use. So conclusion is that a lot of energy could be saved if we are able to design membranes with these pores, not cylindrical pores, but hourglass shaped pores. Well, that brings me to the conclusion. So I hope I convince you that these continuum-based transport models can give impressive results, but it's true that it's mainly if you are interested in a qualitative description of transport, okay? And of course, if you want to be more quantitative, then, or if you want to get insight into the physics of fluids confined inside the system, then you need a much more detailed description of membranes, and then you don't have other choice than going to microscopic modeling into molecular simulations. So these molecular simulations, they are powerful tools, for sure, nothing to say against that, but we have to know, you have to be aware that they require massive computational resource, and that the problem will be the simulation times you can reach. It will be very, very limited. Well, thank you very much for your attention. So as Patrick said, this work was done in Rennes, in the northwest of France. He already said that it's a very nice city. This is a middle-sized city. You are very welcome if you want to visit us. This is the lab and this is the group. Okay, thank you very much for your attention.
नहीं बहुत स्टडी करते हैं